So here's part 1 of chapter 22 on condensations and alpha substitutions of carbonyl compounds. Alpha substitution is the substitution of one of the hydrogens attached to the alpha carbon for an electrophile. The reaction occurs through an enolate intermediate. So here's base. We'll deprotonate the alpha carbon. So this is the carbonyl. Here's your alpha right next to the carbonyl. Electrons will go to that carbon. This is an enolate ion because it actually undergoes a keto-enol tautomerization where electrons from that minus goes to the oxygen, and then when you have it come back down, it'll attack the electrophile to form the new bond. Important thing to note is that you can show either resonance form of an enolate attacking the electrophile in this. What I would prefer you to do is to show it as the O minus, where your electrons are coming down to form the double bond, C double bond O, and then forming the new bond with the electrophile. Condensation of an enolate with an aldehyde or ketone is as follows. The enolate attacks the carbonyl group to form an alkoxide, and so again, here's your electrons and attack the electrophilic carbon. Electrons go to the oxygen. Once you generate this, it'll deprotonate the alcohol to form the product. So this compound is a beta-hydroxycarbonyl compound. You can add to an ester. Esters shown here, again, same mechanism. Now you have that tetrahedral intermediate, but now when your electrons come down from your oxygen, the alkoxide is kicked out, and now you generate a beta-carbonyl compound. Tautomerization is an interconversion of isomers that occurs through the migration of a proton and the movement of a double bond, as shown here, right? So you have, in this case, the keto form, and in this case, the enol form, keto and enol forms. Tautomers are not resonance. It's really important forms. As a result, it's not in brackets. It's shown here. In terms of base catalyzed tautomerization or tautomers, your proton on the alpha carbon is abstracted to form a resonance stabilized enolate ion with a negative charge spread over a carbon atom and oxygen. The equilibrium favors the keto over the enolate ion. So here you're deprotonating, and then you form this this resonance structure in which your electrons from that carbon can go down, and the electrons go to the oxygen over here. This will generate your enol, and then this can get protonated to form the vinyl alcohol. In terms of acid catalyzed tautomers, you can have first protonation of the keto form that will allow then the electrons to move and have a positive charge over here, so that you have a protonated carbonyl, and then the water will pluck it off, forming the enol. So in acid, proton transfers usually occur by adding proton in the new position, then deprotonating the old position. That's important. And then in base, proton transfers usually occur by deprotonating the old position, then reprotonating at the new position. Racemization. So for aldehydes and ketones, the ketone form is greatly favored at equilibrium. So this is the keto form versus the enol. If a chiral alpha carbon, as shown here, so these are the two alpha positions from the ketone, has enolized a hydrogen atom, a trace of acid or base allows that carbon to invert its configuration with the enol serving as the intermediate. This is called racemization. So shown here, under acidic or basic conditions, you form the enol, right, at this position, and then you can racemize from what was the R configuration to the S, and you'll have 50-50. Alpha hydrogens, the pKa for an alpha hydrogen of an aldehyde or ketone is about 20. Much more acidic than alkanes or alkenes. pKa is greater than 40 for alkanes or alkenes, or alkynes, which is actually a pKa of 25. Less acidic than water, which is pKa of 16, or alcohol, pKa of 16 through 19. And only a small amount of enolate ion is present at equilibrium. So if we look at the formation and stability of enolate ions, under basic conditions, you're seeing the alpha hydrogen being plucked off, electrons going to that carbon. Here's your minor form, and then your major form is when you form the enolate, shown here. But really it prefers to be over here, because the pK of the alcohol is 16 to 8, whereas the pK of ketone or aldehyde is 20. Same thing with cyclohexanone. Here's ethoxide, it's deprotonating. Here you're getting the keto-enol tautomers, where you can have, again, electrons go here and electrons go up here. And again, the equilibrium is preferred to on the left-hand side. So in terms of energy diagrams, here's your ketone, your alpha carbon, and your base. Well, it'll deprotonate from the alpha carbon, generating this is the keto form as well as the enol form, and then you have attack on the electrophile to generate your product. So even though the keto-enol tautomerism equilibrium favors the keto form, addition of the electrophile will shift the equilibrium towards the formation of more enol. Synthesis of lithium diisopropylamine, or LDA. LDA is made by using alkylithium reagent to deprotonate diisopropylamine. So here's diisopropylamine. This is N-butyllithium, which we've seen before. This will deprotonate, right? So N-butyllithium, lithium has a positive charge. The butyl group will then deprotonate. So the diisopropylamine has a pK of 40. Butane has a pK greater than 40. As a result, this will go, forming LDA. LDA can convert a carbonyl compound completely to its enolate. So here is cyclohexanone. In the presence of LDA, it'll convert to the enol. So again, this will pluck off. Electrons will go down here and then form the alkoxide. So the enolate is generated, and it's stabilized by the lithium salt. Alpha halogenation of ketones. So we have a ketone in the presence of OH minus. X2 is any Cl2, Br2, or I2. This will generate an alpha haloketone. And so this is called alpha halogenation. Reaction is base promoted rather than base catalyzed, because it's a full equivalent of base that is consumed in the reaction. The proposed mechanism, so the base will deprotonate, electrons will go to that carbon. This will then form the keto-enol tautomer, and then it'll react with the dihalogen to form the alpha halogen product. You can have multiple halogenations, so on the monobrominated ketone you can have, under basic conditions, electrons go there. That will pluck off a bromine, so that now you have a second bromination. So the alpha haloketone produced is more reactive, this is important, than the ketone, because the enolate ion is stabilized by the electron withdrawing halogen. Second halogenation occurs faster than the first, and because of the tendency for multiple halogenations, this base-promoted halogenation is not widely used to prepare monohalogenated ketone. Haloform reaction. Methyl ketone reacts with halogen under strongly basic conditions to give the carboxylate ion and a molecule of a haloform, which is here, shown here. Trihalomethyl intermediate, shown here, is not isolated. And that mechanism is as such: the OH minus base will go attack, electrons go to the oxygen, forming the tetrahedral intermediate, electrons come down, and this will leave. And then you have formed the acid. Now the CX3 minus will deprotonate, so you have a carboxylate ion and a haloform. When you use Cl2, chloroform is formed, Br2, bromoform is formed, and I2, iodoform is formed. So if we look at the iodoform reaction, here's acetophenone in the presence of excess I2 and base. This will form the triiodoacetophenone, and then under the base, it'll form the benzoate and the iodoform. Alcohols can give positive iodoform tests, so that's why it can be used for alcohols. But in this case, it's been used to identify methyl ketones. And iodoform itself, that's formed, is a yellow solid that will precipitate out of solution. So let's do a problem. Propose a mechanism for the reaction of 3-pentanone with sodium hydroxide and bromine to give 2-bromo, 3-pentanone. So first step, hydroxide will deprotonate, electrons will go onto that carbon. This can undergo tautomerization, right, to form the enolate ion, shown here. This can attack directly, right? Electrons will go here and attack the bromine, or as such, to form the alpha haloketone. Acid catalyzed alpha halogenation. Here's your acetophenone in the presence of bromine and acid will generate alpha bromoacetophenone and HBr. If you add chlorine to that same molecule in acetic acid, you'll generate the dichloroacetophenone and HCl. The reason why it's the dichlor is because you're adding two equivalents. Mechanism of the alpha halogenation that's acid catalyzed. First step is you're going to protonate, so this is showing it as the enol already. So from here, it's already been protonated. Now electrons come down, attack the halogen, forming this keto form, and then you have electrons quenching that positive charge, and now you have this carbocation. Then the halogen ion will attack the H. Electrons will then come down to form the alpha haloketone. Propose a mechanism for this question for the acid catalyzed conversion of cyclohexanone to 2-chlorocyclohexanone, shown here. So first step is it's going to protonate. Once it protonates, you can then form the resonance structure, shown here, where your electrons then go to the oxygen and you form that carbocation. Once that form, your base will then come, deprotonate, electrons will go and form the enol. Once the enols form, then your electrons come down. This will attack the chlorine, split it up. Again, another resonance form is shown here, in which your electrons now go quench that positive charge, and now you have your chlorine minus, deprotonate, electrons will go to the actual down here to form the double bond, forming the alpha chloro result. Here's the Helvold-Zielinski reaction, or HVZ. Here you have a carboxylic acid in the presence of Br2PBr3, which we've used before, and then in this case will form an alpha bromoyl acyl bromide. In the presence of water, that bromine gets replaced with OH, generating the alpha bromo acid. So the HVZ reaction replaces a hydrogen atom with a bromine atom on the alpha carbon of a carboxylic acid. The acid is treated with bromine and phosphorus tribromide followed by the hydrolysis to convert that bromide into the bromo acid. So let's look at the mechanism. The first step is the bromination of the acid, so you form the acyl bromide. Once you form the acyl bromide, this is the keto form. It can also form the enol form, shown here. And this is under equilibrium. The enol form is nucleophilic, so then it attacks, so then electrons come down. Double bond will go attack the bromide, forming the alpha brominated product, and then the Br counterion will then deprotonate, forming the alpha bromo acyl bromide. And then that will subsequently react with water to form the acid. So you can alkylate enolate ions. So here's your keto enol tautomer. Here you can attack the CH2. So by SN2 reaction, kick this off. This is C alkylation. You can actually, from the O minus, actually attack, do the same thing, and this would be O alkylation. So the reaction usually takes place primarily at the alpha carbon, so this is preferred, forming the new CC bond, and this is less common. So alpha alkylation of enolate, so you're going to add LDA, that will deprotonate this, and then that will then attack this via SN2 to generate your new CC bond. Enamines, so ketones or aldehydes react with secondary amines to form what are called enamines. The enamine has a nucleophilic alpha carbon, as you can see, so when you generate this, you can have electrons then from your nitrogen come down and then go to the carbon, so that you can now use this source to attack electrophiles. If we look at an electrostatic potential map of an enamine, here's a pyrrolidine enamine of a cyclohexanone, and shown here is your electrostatic potential, where the red part is near the alpha carbon of the double bond. This is that nucleophilic carbon, shown here. So when you have your ketone or aldehyde react with a secondary amine, right, that's the first step. Electrons go out, and then you have a transfer of protons to generate this product. Then you have OH will take the proton and generate a good leaving group, in which your electrons from your nitrogen will come down and the water will leave. This will generate a resonance form, shown here, where you can have electrons come in and form the double bond, vice versa. Now, once you're at the stage, you can have water come in, and water can remove a proton from the alpha carbon, generating the enamine, and it doesn't react with that R group. So you can alkylate an enamine. So once you generate the enamine, your electrons from your nitrogen come down. This will attack, do an SN2 reaction to form a new bond. This is an alkylated iminium salt. In the presence of protonated water, though, this will then remove the iminium salt and generate the ketone, so that it becomes the alkylated ketone. So let's look at the acylation of enamines. Here your nitrogen electrons come down, attack, electrons go to the oxygen, forming the tetrahedral intermediate. Oxygen comes down, kicks off the chlorine. This generates an acylaminium salt. When you add protonated water, this will replace this with ketone, so it becomes a beta diketone. Condensation of ketones and aldehydes. Condensation combines two or more molecules, often with the loss of a small molecule such as water and alcohol. Aldol condensation, which is important, is the addition of an enolate ion to another carbonyl group. This occurs under basic conditions. Let's look at an aldol condensation. Here you have a ketone or aldehyde and another ketone or aldehyde, and what happens in the presence of acid or base is that you're taking your alpha and then reacting it to the carbonyl center, so this becomes an alpha beta hydroxy ketone, or the aldol product. And then when you subject it to heat in the presence of acid or base, this will then eliminate to form an alpha beta unsaturated ketone, so this alpha beta unsaturated ketone. So if we look at the base catalyzed aldol condensation, the first step is deprotonation of the alpha carbon, forming the enolate ion, right? So you can have electrons go down this way and over to the oxygen. And then as your electrons are coming down, this will attack, right, the carbonyl, and the electrons will go to the oxygen. Once you form the new bond, this will protonate from whatever's in the solution, generating, in this case, the alcohol generating alkoxide. And then this will generate the aldol product. You can do acid catalyzed reaction. In this case, your electrons from your oxygen will protonate, forming the protonated carbonyl. You can then have electrons go to your oxygen, forming the carbocation. Then your water will deprotonate, forming the double bond, forming the enolate or enol. Once the enols form, your electrons from your oxygen come down, attack the electrophilic carbon center of the other ketone that is already protonated, right? Electrons go there. Here you have resonance stabilization, in which your electrons move to the oxygen, so now you have your carbocation. You can have the alcohol that's in the system deprotonate, electrons go to the alcohol so that you generate the aldol product. So you can drive aldol condensation to completion by using the system, the setup where you're condensing, you're cooling down the acetone vapor so that you can allow for this reaction to occur. Because if you're looking at the reaction of two acetone molecules, the formation of the diacetone alcohol is very little, as you can see. So to drive this, you can set up your reaction this way. Dehydration of aldol products. So under acid or base and heat, you can eliminate water so that you form a new double bond and form that alpha beta unsaturated aldol. So when the enolate of one aldehyde or ketone adds to a carbonyl group of a different aldehyde or ketone, this results in a cross-aldol condensation. So here's a propanol, here's an enolate of ethanol, it's going to attack, this is your product. You can have enolate of propanol add to ethanol, so here's attacking, forming the product here. You can do a self-condensation of ethanol and propanol, which we've seen before. So this ends this part of this chapter.